Hi everyone, I'm Xian-Min Jin from Shanghai Jiao Tong University, and I'm a director of Center for Integrated Quantum Information Technology, and also founder and CEO of TuringQ company. Today, deliver a talk titled Photonic Chip for Scalable Quantum Information Processing. So this is an outline. Guys, you all know about the new track in post-Moore year. And I will introduce a bit. So we know electric circuit is follow the Moore law for quite a long time. The people think about after the Moore's law, what kind of ability we can develop to extend the computational power for humankind. So Nature published a review and point out optical, quantum, and even DNA computing. And this kind of new architecture probably can be the opportunities. So my group is working on quantum computing, photonic computing, and also optical AI. And also we believe device can contribute to optical communication and optical interconnection, and that probably also can contribute to the computational resources. But all this technique highly depend on the system size, how large, the photonic system we can operate, no matter quantum computing, but also the photonic computing and also quantum AI. So chip-based and integrated approach is very appealing method towards developing large-scale quantum and optical systems. We know the quantum race corporations include very large companies like IBM, Google, Honeywell, and also some new startup company like D-Wave, IonQ, and PSIQ, and also our company, TuringQ. So this is the race, but also the contribution from all this company to extend the computational power for humankind. IDC gives a report about the size of the enterprise quantum computing market, and that shows it can reach like 9 billion 2020. It also gives the size in terms of different region like Europe, Asia Pacific, and North America. So this report is very encouraging and also impressive, and especially to our startup company. So we know the quantum computing is still in a very early stage, but the future is very encouraging. And we know that there's many different physical implementation like photonics, trap ions, neutron atoms, superconducting loops. Different physical implementation has different advantages and also disadvantages. So like qubits connected, the scales, and also the fidelities, so error correction, the gate circuit model capability. For photonics, luckily, it has no apparent drawback. So we believe, and also it can work in room temperature, and also it can scale up by using integrated photonic chip. So we believe photonics implementation can be very promising, and in the future it probably also can reach like a cloud platform, also a terminal platform. So so that's why we have started research in this area 10 years ago, and now we found our TuringQ company. So about quantum supremacy or quantum advantages, John Preskill gives this name about quantum supremacy. It also defined the turning point about the competition between quantum computing and classical computing. And we can clearly see that after the turning point of quantum supremacy, the quantum approach will beat classical approach in a completely new way, and the exponential scaling will change the game. That's very encouraging, and we know recently Google and a team from USTC has shown that it's possible to reach this point, and after that we will have to think about what kind of applications, even if it's only specific applications, we can reach the quantum supremacy. So 2013, I and my colleagues in Oxford, we performed the first boson sampling experiment, and that was published on Science. We got a lot of coverage because people believe this is very straightforward and it's a shortcut to quantum computing. For boson sampling problem, we only need to prepare a photonic network, and we prepare a single photon source and inject into this kind of network. We detect the multi-photon correlation after the chip, and that's all. This is the machine, and this machine can solve the problem for like a boson sampling or boson sampling related problems. So we don't need like a high fidelity gate, and we don't need error correction. So we got a lot of coverage, and since 2013, many groups all over the world performed boson sampling experiment and also proposed many very cool ideas about the applications and also some variant boson sampling protocols, especially a protocol proposed by a German group. It's called Gaussian boson sampling. And we know recently a group from USTC, they perform 100 photon level Gaussian boson sampling and beat the classical computing with many times and with many order higher. So we performed the first boson sampling, and we also collaborate with a group from NUDT, National University of Defense Technology. They have the tenured supercomputer, and that's maybe 2017 or 2018. And that time, tenured is the most or fastest supercomputer in the world, and I think it was ranked at the top 1 for like 6 times. So we collaborate with a group from NUDT, and we test boson sampling with tenured 2 supercomputer, and the test shows that 50 photons will saturate the tenured 2 supercomputer. So you can see the supercomputer is very powerful, but when quantum computing reach that area, it will completely change the rules. Like 51 photons will equal to 2 tenured supercomputer, and 60 photon will equal to 1,000 tenured supercomputer. That's what supercomputer and the quantum computer shows. For photonic computing, previously people only work on the macroscopic optics. From 2010, many groups are working on quantum integrated photonics. UK also launched a very big fund called IQIT, and my previous group in Oxford, led by Professor Ian Walmsley, win one of the 4 funds. It's huge money, and that's probably the origin for the emerging quantum integrated photonics. Back to Shanghai Jiao Tong University. So you can see the previous experiment performed in Bristol, in Oxford, or in Rome. All the photonic chip, the photonic circuit located 1 layer. And we performed the experiment like quantum gate, boson sampling, quantum teleportation, quantum walk. But we can still see some drawback and also all limitations. We thought about some new strategy, like what the dimension means, what the number of the mode means. And we know the increased photon number, we can increase the Hilbert space very efficiently. And from the picture left, you can see increase the dimension. It also can be very efficient to increase the complex of the quantum system. And if we also increase the photon number, the quantum system can go very large. If the size of the quantum system not only 4, is 15, 25, or 50, from the right side, you can see the quantum system can scale up to very large level. For every site, we can change the properties and we can tune in the beta. And for the coupling between each two sites, we can change the geometric relationship and we can tune in the Cij. So the Hamiltonian can be tuned very freely in 3D structure, and we can freely design the Hamiltonian, and we basically can fabricate this kind of Hamiltonian chip with some 3D fabrication method. And also we plan to increase the number of the mode we can reach the power of the conventional computer with a better way. So the method is called femtosecond direct writing. It's invented last century. The problem is this kind of fabrication is not very stable. The chip is not fabricated step by step, so it just fabricated with one shot. For the one shot fabrication, what the parameter is decide what the performance we can get. But this kind of fabrication has a relationship to many, like more than 10 different parameters. So, and these parameters probably fluctuate, like frequency and laser pointing, and also temperature, amplitude fluctuation. So all these parameters are key to the performance of the chip. So we try to lock everything, lock all the parameters, and our system is quite complicated. And we try our best for 4 years, and we made it. We lock every parameters. Now our setup can write largest 3D photonic chip, and also can reach the performance freely. Repeatably. So this is a big achievement. We can fabricate as design, and we only need to focus more on the literature searching, focus more on the ideas and design. And for the fabrication, we can do fabricated as design, and we can map the idea to the chip with very certain way. The second photonic chip we are working on is called LNOI, programmable photonic chip. So this is a new technique. It's similar to the silicon on insulator, but the materials is lithium niobate. We know lithium niobate is very good materials, but it's very hard to make photonic chip. Now the Chinese company now can prepare the film on the insulator, and we only need to work on the fabrication. So this photonic chip can be much faster than silicon chip, and also in terms of the spectrum, applied spectrum, and also the loss, all better than silicon chip. So we contribute most of our time and funds to this kind of chip since 2018. So including the 3D photonic chip and LNOI programmable chip, we have the photonic chip platform in our group, and also we have like a 20 years quantum information experience. So we, as a group, have both the photonic chip and also quantum information platform. So we can make the quantum information, on-chip quantum information tasks very quickly. Now we have our own feature. We have the 3D photonic chip and LNI programmable chip, and our university also support my group by launch a new center called Center for Quantum Integrated Technologies, and also our work get a lot of coverage. So we achieved many very good advances in the frontier and applied research. So we construct a large-scale photonic chip with 3D structure, and we performed the experimental 2D quantum work on a photonic chip, and that's published on the Science Advance. We also design a hexagonal graph structure, and we prove that structure can achieve the very efficient quantum fast heating algorithm. This work published on the Nature Photonics and got a top 10 breakthrough in optics in 2018. And also we learn how to map SSP problem called a subset problem. It's an NP complete problem to photonic chip, and we also borrow some techniques like a single photon detector, and also this is a non-Phenomen architecture. So all these together, 3 features together, we demonstrate scalable photonic computing, and this work shows that this machine has a better computational power than the Intel Pentium 4. Now we are working on the bigger problem size, like a 10 layer, and for that size we can reach the Intel Core i7. This is quite promising photonic computing approach. We only borrow a little bit quantum feature. Of course, we also can reach some like quantum simulator by using our 3D photonic chip. For example, we fabricate fractal networks in our 3D photonic chip, and we know the light can involve in this kind of network very easily, and even we can make the single photon detector with this kind of system. So we achieved the first observation of quantum transportation in fractal networks. We know the fractal networks exist in the natural environment, like some leaves or neural network. And even people believe that the neural network or our brain has some ability enhanced by quantum interference or quantum technologies. We don't know because the brain is very hard to access, and our experiments show we can build a fractal network and we can perform some observation of like quantum transportation. So this is a very typical quantum simulator. We can simulate some system that we cannot access right now. Besides the quantum simulator or analog quantum computing, we also work on like a photonic chip to take the power of the multi degree of freedom. For example, OAM, orbital angular momentum. So this kind of degree of freedom is very powerful because in principle it has infinite dimensions. So this kind of degree of freedom can be mapped in and mapped out in some like donut-shaped waveguide. in fiber, because fiber we can fabricate this kind of structure, but for chip it's very hard. By using the 3D laser writing, my group, we managed to write this kind of donut-shaped waveguide, and this work was confirmed as the first promising step towards integrated structure for OM carrying light. We only published 2 papers now, but our work all published on physical review later, and got a coverage on the APS website and also physical world. Even our free comments and editor comments on that. This is a very technical work, but it's so important it should be published on physical review letter. And after 2018, we performed the second experiment. Not only mapped the OM state in and out, we make the coupling between a single mode fiber or a single mode waveguide on chip and also OM waveguide on chip. So the coupling can transfer a single mode to OM mode. So, and the efficiency can reach like 70%. So it's quite high. And now we are working on like near unity efficiency emitter. So this coupling in principle can be like 100%. So it's very encouraging, and we believe this method can be more efficient than the bulk optics method, like use a special light modulator chip, OM carrying waveguide chip, and OM emitter on chip can be more efficient than the bulk optics. So this is not only more integrated, but also more efficient. So it's very encouraging. Besides, for different degree of freedom, for the operation itself, we also manage to protect the quantum operation by using the topological physics. Of course, we also use some like symmetry-induced mechanism. We know the topological physics can be observed or designed and observed in the different system, but only for optical system we can detect the field at the single particle level. So quantum photonics plus topological physics, there's an emerging field, quantum topological photonics. I mean, in this emerging field, we can probe topological physics at the level of single particle. So we achieved the first direct observation of topology from the single photon dynamics. And we also observed the parity-induced thermalization gap on the chip. And also we have a very, very simple idea, use the localization effect of topological physics to protect the quantum state against the diffusion-induced loss. We know that loss is decoherence, right? So we perform a series of work, including protect single photon state, protect two photon quantum correlation, and also protect quantum superposition and entanglement. And recently, we also managed to realize error filtering with symmetry-induced mechanism in photonic Lib lattices. So as this is a series of work get a quite good not only publication, but also we define a new emerging research field, and that show some very fundamental phenomena can be very useful for quantum information processing. Ian Osborne, editor Ian Osborne from Science, write a highlight entitled "Protecting the Quantum" and give a very good highlight for our works. We know this single photon can get lost, and some gate is not deterministic. Quantum memory and a quantum network with feedback is very important for photonic quantum information processing. We can use the cold atom, we can use some solid quantum memory, but in a cryogenic system. That's approach can be very quiet. The system can be very quiet, very clean, and even sometimes can be very efficient. But the physical system itself is very large and it's very hard to scalable, and also it's very hard to fit to real application. So we developed the room temperature and broadband quantum memory and quantum network in cesium atomic cell. So our work was published on the Optica Science Advance and Quantum Information, MPJ. So this is the work shows that it's very promising to, also it's possible to map the single photon in and out the atomic cell. And we can retrieve them on demand, and with this operation we can do some feedback, and we can coordinate the different gate, quantum gate or quantum source. We can synchronize multi-photons, or we can synchronize the quantum operations, and can make the non-deterministic photonic quantum information to deterministic quantum information processing by the buffer, by the coordination. So this is one effort we have made along this way. We also try to combine the AI technology and the quantum information, and we performed experiment, I think, in the very early stage, like 2018. We probably the first group to, in that time, there's another group from Italy. We together, Italy and UK, yes, and we together got an idea, also simultaneously got an idea about the enhancement of the quantum tasks by using AI techniques. So we know we can classify like apple and orange by AI, but actually this technique can be extended to quantum tasks, like entanglement state is inseparable or entangled. Apply this AI technology, and it works very well. So we perform the tomography, we use the PPD character criteria, and we feedback the result to the artificial neural network. So after the training, and we can prepare arbitrary state, and then artificial neural network can tell the new input state is entangled or separable. So this is a very interesting work. And also we invent a quantum Go game, and this game we performed the Go game by put the entangled stone, and only the new entangled stone touched, and then the entangled stone will, both of the pair of the entangled stone will collapse, and the collapse position is a very random, and so this kind of game increase the space, increase the set size a lot. For example, for 36 to by 36 quantum Go, the number of the information set can go to 10 to 618. So for this kind of game, I think for the classical AI probably cannot be very powerful because the space is so large and it's very hard to get trained. Quantum Go can be a very good platform for test platform, like a two AI machine, or AI and a humankind, or two humankind. So because the size is so large, and we don't know who will win the games. So it can be a benchmark platform, and it's very interesting. My group also put all our code and launched the first photonic quantum computing software. That software can allow any clients to run the analog quantum computing algorithm, and this work will bridge some engineering who don't know quantum optics so that much, and also some application tasks. So this can be a very good bridge for the application side and the fundamental research side. So yeah, with all these developed techniques and achievements, we believe emerging industry is arriving, and our TuringQ company aim to develop the 3D and ultra high speed photonic quantum computing chip, and we aim to develop a photonic computer, and AI will show the computational power or the better power consumption superior to classical computer. And this company is the first photonic quantum computing in China, and it got quite good support from the capital and also local government. Fully integrated analog photonic quantum computer, and that's a commercial and also for research. That's fully integrated means it includes the light source, photonic chip, and detector, and also the software. So our photonic quantum computer that include the photonic chip algorithm and system, and also the light source. All these systems quite commercial and very easy to access. And the light source is quite bright, the fidelity quite high. Of course, the weight is still very high, but our next generation will be very, very small. The loss and the precision and the layer of the 3D photonic chip, that's all marked the quite high level in the field of the analog for the photonic quantum computing. And any research group can develop some algorithm and also some specific applications by using our machine, and that machine can help for this stage, can help for the research and development. It has the computational power superior to classical computer, but can be very good research platform for R&D. And our company also has many very unique techniques. For example, like a photonic filter modular. That modular have integrated 3 FP cavities, and that cascaded system can help to reach like 10 to 7 to 1 extinction ratio, and for very large applied spectrum. And so this kind of modular cannot be gated in the market. So its applications include not only in quantum computing, but also for like imaging and material science, and also biological, medical imaging, and also aerospace industry. And similar techniques we can extend to high resolution multicolor beam splitter system, and that system can be very, very useful for splitting 2 specific spectrum with very high extinction rate. And we know the bulk optics diachroic mirror that work for like a nanometer or terahertz level, and for our system it can reach to megahertz level. So that's improvement is very powerful. For the quantum software, we realize Farman packs I just mentioned in my group. We have already realized Farman packs 2018, but that was developed in MATLAB. now rewrite the code and by use Python, and now the file packs can be commercial and also be visited online with a cloud platform architecture. I mean, many users can use file packs. We also developed quantum means by algorithm for application, and I have already introduced Quantum Go, and that now is also online. And we developed Deep Quantum. I will introduce later, and we are working on our own TuringQ OS system. Yeah, so our architecture is quite this photon is quite complicated, but that means we are developer the full track for photonic and quantum computing, including the algorithm, including the hardware structure. The hardware structure, you can see that in CPU, QPU, and FPGA, and specific tasks, quantum machine like ISO machine, they all can work together and coordinate together. This heterogeneous computing architecture can be very useful and very easy to access. The deep quantum is very key to connect the application side and also our hardware. So we are now working on that, and we hope this deep quantum structure, deep quantum layer can help the user to use our hardware structure, and we hope to share all this on Quantum Cloud. Try to collaborate with some top company like AWS. For the application side, for example, we use quantum reinforcement learning for oriented synthesis of photovoltaic materials with high photoelectric conversion efficiency. That shows that quantum machine learning can be more efficient than the classical machine learning. So for the application, not only this, we also work on the fintech, AI, and also big data area. So I think we have no time to go through all this algorithm, but many research shows that it's quite promising in this region. Well, we also pay attention about some quite lower application like photonic TPU and also optical artificial neural network, and we, as I mentioned, we probably can show the supremacy with only photonic system, with only photonic computer, not a photonic quantum computer. Our 3D fabrication can be very useful for many fields, not only for quantum computing. And our algorithm developed for ARC quantum computing or quantum communication. Recently, we focus more on the ARC optical communication, and we reach 160 dB world record for ultra-high loss communication by inventing a new protocol. We call it photon intercorrelation protocol, and that 160 dB loss is 40 dB better than previous world record. So this algorithm, of course, our system also hardware system also improve a lot. So quantum hardware system and also the newly invented the quantum algorithm help to reach the 160 dB world record, and that can be very useful for ARC optical communication and also for like a Chinese version of the Starlink program, also for deep space optical quantum communication, like from Earth to Mars. We know the diffraction limit, the light beam will become very large if we try to realize optical communication from Earth to Mars. And that will introduce very huge geometric loss. And our 160 dB can help this deep space optical communication. And we only need a very limited size of the telescope, like 20 centimeter, and for both terminals, and we can reach this deep space optical communication. Yeah, so this is my group in Shanghai Jiao Tong University, and this is my group in TuringQ. We're still on our way to photonic quantum computing and or photons related computing power. We hope we can be very brave and a pioneer towards quantum enhanced computing architecture. Thanks a lot. Yeah, this is my email and telephone number, and I'm happy to discuss with colleagues all over the world and about the opportunity on applications and also some collaborations on business. Thanks a lot.